Okay, we're back in Unit 2 looking at some speed versus velocity. Now, both of these might be terms that you've heard of before, speed and velocity. But just like with distance and displacements, we need to start thinking about scalar quantities versus vector quantities because speed and velocity are very, very different. A speed, which I will traditionally write out as just a v, kind of a little curl to it. A speed is just like how fast you're going. I'm going 10 miles per hour. I'm moving at 7 meters per second. It is just a distance divided by a time. On the other hand, a velocity, which we'll write with that same curled v, but with a vector arrow over the top of it, is your speed and the direction you're traveling. So where a speed might just be like I said, 15 meters per second, a velocity would be 15 meters per second north or south or east or west. It has a direction to it. It could be pointing this way, okay? This matters within the world of physics for very, very specific things that we do because we can move both forward and backwards on a day-to-day basis. You can move in a positive and negative direction. And not only that, you can move left and right, but you can also move up and down, and you can also move forward and backwards. So depending on how you're moving in 3D space, this idea of a velocity having a direction associated with it becomes very, very powerful. Okay? So if we take a look at this, traditionally when we think about velocities, if we just look at our units here, it is some amount of distance divided by a time, or if we'd like to think about if we're looking at the vector component, that would be a displacement instead over an amount of time. But it is like a amount you've traveled divided by some time interval, okay? And a traditional equation for velocity we have is right here, velocity, and these are all, can be thought of as either vectors if you're doing velocities, or if you're looking at just speeds, they can be thought of as displacements, is just this distance or displacement divided by some time for speed or velocity. Now, when we're looking at this equation, this velocity is not changing at all right now. This is an averaged velocity. We're not speeding up, we're not slowing down. We're just saying, hey, look, this is how far you've gone, this is how long it's taking you to do that. I don't know if you went very, very fast in the beginning and then you slowed down at the end because you got tired. I don't know if you were nice and steady throughout. I don't know. But so we call this like an average velocity here. But if we look at the little example we have, let's start with a little picture as we're doing this. Pictures are always super nice, as Grandpappy Botzer will tell you. You're driving down a street at 56 kilometers an hour. So this is my beautiful car I'm drawing. I feel like Mr. Botzer, this is the worst car ever. You're right. This is you somehow standing in your window. Don't ask. We'll make the car red because that makes it go faster. Oh, but a child has run out into the road in front of you. So let's draw a tiny child. Don't hit me. Put a bow in their hair. See, little child. I don't know what that is. That looks like a weird fish now. Whatever. But if your reaction time is 0.72 seconds, how many meters have you traveled before you even hit the brakes? Like, what's your reaction time? And, did you just hit this kid? So how far have you traveled before you even hit the brakes? So let's just kind of highlight some of the things we have in this problem and look at what we have here. So we're driving down the street at 56 kilometers per hour. So that is our speed or velocity. We can think of it as either speed or velocity because it's in one direction. So let's just say this is our velocity and it's 56 kilometers per hour. We know the time that it takes for us to react is 0.72 seconds. And what we're looking for is this distance traveled. So we're looking for a delta x. So I'm looking for this delta x up here, which means I need to rearrange this equation. I like to rearrange equations first before I put my actual numbers in there. The reason why I like to do this is because if I set the equation up correctly, but then I just like mess up a number, I at least know that I'm doing the physics right, and the rest of it is just blah, math, number nonsense. So if I have v equals delta x divided by t, and I need to move this delta x so it's by itself. That means I need to get rid of this t on each side. So I'll multiply by t, boink boink, and that means I multiplied by t on the other side. So what I now have is that the velocity multiplied by time will equal the delta x. And now I just have a little bit of a headache because if I notice this, my velocity is in kilometers per hour and my time is in seconds. Woof. So I might need to do a teensy-weensy little bit of a unit conversion up here on the velocity. So let's do that real quick. Let's just pull this over here. So we've got 56 kilometers per hour. Train track that. To get this in meters, there are 1,000 meters in 1 kilometer. Boink, boink. And then how many seconds are in an hour? Well, in 1 hour, there are 3,600 seconds. So boink, boink. And this means that my velocity will have a new value if we churn this out of 56,000 divided by 3,600. My velocity is about 15.56 meters per second. And I've kind of ignored some of the sig figs here. I'm not super worried about that. I really care about the physics, less about the sig figs. So here's our velocity. And that's in meters per second. And that means I can multiply it by seconds to get our delta x in meters. So let's do that now. We can say 15.56 meters per second times the time of 0.72 seconds. The seconds are going to cancel and divide out. Will give us our delta x. And our delta x in this case is 11.2 meters. Which, if you're like, well, how far is 11.2 meters? Meters about 3 feet. So before you even touched the brakes, your car went about 30 feet. Which means that hopefully that kid was further than 30 feet away from you. Things start getting really iffy, though, when that was just how long it took for you to hit the brakes. Your car hasn't stopped yet. And if you're going 56 kilometers an hour, which is somewhere between like 30 and 40 miles per hour, you still need to stop. You're going to go further. You're probably going to hit this kid. Which, this reaction time of 0.72 seconds, that's pretty much the reaction time for whenever people look down at their phone and then look back up. So if you're looking at your phone in a car and something darts out in front of you, good luck. You're probably going to hit it. Okay? So it's very important for all you new drivers out there to pay attention to the road. This is how we can make use of a velocity or a speed equation, depending on if you have a scalar or a vector quantity, and just how we can kind of manipulate the equation to solve some values out. But with that, this is finished. Go try some practice problems. We'll be talking about a slightly more complicated average velocity in one of our future videos. Until next time, adios.